Nondestructive testing or nondestructive testing is a wide group of analysis techniques used in science and industry to evaluate the properties of a material, component or system without causing damage. The terms nondestructive examination, nondestructive inspection, and nondestructive evaluation are also commonly used to describe this technology. Because NDT does not permanently alter the article being inspected, it is a highly valuable technique that can save both money and time in product evaluation, troubleshooting, and research. Common NDT methods include ultrasonic, magnetic particle, liquid penetrant, radiographic, remote visual inspection, eddy-current testing, and low-coherence interferometry. NDT is commonly used in forensic engineering, mechanical engineering, electrical engineering, civil engineering, systems engineering, aeronautical engineering, medicine, and art. Methods. Ndt methods may rely upon use of electromagnetic radiation, sound, and inherent properties of materials to examine samples. This includes some kinds of microscopy to examine external surfaces in detail, although sample preparation techniques for metallography, optical microscopy and electron microscopy are generally destructive, as the surfaces must be made smooth through polishing or the sample must be electron transparent in thickness. The inside of a sample can be examined with penetrating radiation, such as X-rays or neutrons. Sound waves are utilized in the case of ultrasonic testing. Contrast between a defect and the bulk of the sample may be enhanced for visual examination by the unaided eye by using liquids to penetrate fatigue cracks. One method involves using dyes, fluorescent or non-fluorescent, in fluids for non-magnetic materials, usually metals. Another commonly used NDT method used on ferrous materials involves the application of fine iron particles that are applied to a part while it is in an externally magnetized state. The particles will be attracted to leakage fields within the test object, and form on the object's surface. Magnetic particle testing can reveal surface and some subsurface defects within the part. Thermoelectric effect uses thermal properties of an alloy to quickly and easily characterize many alloys. The chemical test, or chemical spot test method, utilizes application of sensitive chemicals that can indicate the presence of individual alloying elements. Electrochemical methods, such as electrochemical fatigue crack sensors, utilize the tendency of metal structural material to oxidize readily in order to detect progressive damage. Analyzing and documenting a non-destructive failure mode can also be accomplished using a high-speed camera recording continuously until the failure is detected. Detecting the failure can be accomplished using a sound detector or stress gauge which produces a signal to trigger the high-speed camera. These high-speed cameras have advanced recording modes to capture some non-destructive failures. After the failure, the high-speed camera will stop recording. The capture images can be played back in slow motion showing precisely what happened before, during and after the non-destructive event, image by image. Applications: weld verification. In manufacturing, welds are commonly used to join two or more metal parts. Because these connections may encounter loads and fatigue during product lifetime, there is a chance that they may fail if not created to proper specification. For example, the base metal must reach a certain temperature during the welding process, must cool at a specific rate, and must be welded with compatible materials, or the joint may not be strong enough to hold the parts together, or cracks may form in the weld causing it to fail. The typical welding defects could cause a structure to break or a pipeline to rupture. Welds may be tested using NDT techniques such as industrial radiography or industrial CT scanning using X-rays or gamma rays, ultrasonic testing, liquid penetrant testing, magnetic particle inspection, or via eddy current. In a proper weld, these tests would indicate a lack of cracks in the radiograph, show clear passage of sound through the weld and back, or indicate a clear surface without penetrant captured in cracks. Welding techniques may also be actively monitored with acoustic emission techniques before production to design the best set of parameters to use to properly join two materials. In the case of high-stress or safety-critical welds, weld monitoring will be employed to confirm the specified welding parameters are being adhered to those stated in the welding procedure. This verifies the welder's correct procedure prior to non-destructive evaluation and metallurgy tests. Structural mechanics. Structure can be complex systems that undergo different loads during their lifetime. Some complex structures, such as the turbomachinery in a liquid fuel rocket, can also cost millions of dollars. Engineers will commonly model these structures as coupled second-order systems, approximating dynamic structure components with springs, masses, and dampers. The resulting sets of differential equations are then used to derive a transfer function that models the behavior of the system. In NDT, the structure undergoes a dynamic input, such as the tap of a hammer or a controlled impulse. Key properties, such as displacement or acceleration at different points of the structure, are measured as the corresponding output. This output is recorded and compared to the corresponding output given by the transfer function and the known input. Differences may indicate an inappropriate model, failed components, or an inadequate control system. Radiography in medicine. As a system, the human body is difficult to model as a complete transfer function. Elements of the body, however, such as bones or molecules, have a known response to certain radiographic inputs, such as X-rays or magnetic resonance. Coupled with the controlled introduction of a known element, such as digested barium, radiography can be used to image parts or functions of the body by measuring and interpreting the response to the radiographic input. In this manner, many bone fractures and diseases may be detected and localized in preparation for treatment. X-rays may also be used to examine the interior of mechanical systems in manufacturing using NDT techniques, as well. Notable events in early industrial NDT: 1854 Hartford, Connecticut, a boiler at the Fales and Gray Car Works explodes, killing 21 people and seriously injuring 50. Within a decade, the state of Connecticut passes a law requiring annual inspection of boilers. 1880 to 1920 The oil and whiting method of crack detection is used in the railroad industry to find cracks in heavy steel parts. This was the precursor to modern liquid penetrant tests. 1895 Wilhelm Conrad Ra paragraph NTGEN discovers what are now known as X-rays. In his first paper he discusses the possibility of flaw detection. 1920 Dr. H. H. Lester begins development of industrial radiography for metals. 1924 Lester uses radiography to examine castings to be installed in a Boston Edison Company steam pressure power plant. 1. 1926 The first electromagnetic eddy current instrument is available to measure material thicknesses. 1927 to 1928 Magnetic induction system to detect flaws in railroad track developed by Dr. Elmer Sperry and H. C. Drake. 1929 Magnetic particle methods and equipment pioneered. 1930s Robert F. Mell demonstrates radiographic imaging using gamma radiation from radium, which can examine thicker components than the low-energy X-ray machines available at the time. 1935 to 1940 Liquid penetrant tests developed. 1935 to 1940 eddy current instruments developed. 1940 to 1944 Ultrasonic test method developed in USA by Dr. Floyd Firestone, who applies for a U.S. invention patent for same on May 27, 1940 and is issued the U.S. patent as grant number 2,280,226 on April 21, 1942. Extracts from the first two paragraphs of this seminal patent for a non-destructive testing method succinctly describe the basics of ultrasonic testing. My invention pertains to a device for detecting the presence of inhomogeneities of density or elasticity in materials. For instance, if a casting has a hole or a crack within it, my device allows the presence of the flaw to be detected and its position located, even though the flaw lies entirely within the casting and no portion of it extends out to the surface. The general principle of my device consists of sending high-frequency vibrations into the part to be inspected, and the determination of the time intervals of arrival of the direct and reflected vibrations at one or more stations on the surface of the part. 1946 First neutron radiographs produced by Peters. 1950 The Schmidt hammer is invented. The instrument uses the World unregistered trademark S first patented non-destructive testing method for concrete. 1950 J. Kaiser introduces acoustic emission as an Ndt method. Basic source for above, Hellier, 2001. Note the number of advancements made during the WWII era, a time when industrial quality control was growing in importance. 1963 Frederick G. Weighart's and James F. McNulty Euro unregistered trademark S. co-invention of digital radiography is an offshoot of the pair's development of non-destructive test equipment at Automation Industries, Incorporated, then, in El Segundo, California. See James F. McNulty also at article Ultrasonic Testing, 1996 Rolf Diedericks founded the first open-access NDT journal in the Internet. Today the open-access NDT database ndt.net, applications, NDT is used in a variety of settings that covers a wide range of industrial activity, with new NDT methods and applications, being continuously developed. NDT services are not only integrated with asset integrity management solutions, but also with material testing laboratories and seamlessly fit into supply chain services. Automotive, engine parts, frame. Aviation maintenance companies use non-destructive testing to inspect or detect cracks, flaws or imperfections in engine parts. Aerospace, airframes, space frames. Power plants, propellers, reciprocating engines, gas turbine engines. Rocketry. Construction, structures, bridges, cover meter. Maintenance, repair and operations, bridges. Manufacturing, machine parts, castings and forgings, fabrication inspection. Industrial plants such as nuclear, petrochemical, power, refineries, pulp and paper, fabrication shops, mine processing and their risk-based inspection programs. Pressure vessels, storage tanks, wells, boilers, heat exchangers, turbine bores, in-plant piping, full storage tank assessment, shutdown inspections, in-service equipment inspections. Miscellaneous, pipelines, in-line inspection using PIGs, pipeline integrity management, leak detection, pipeline open data standard, ASME pressure vessel and piping as built inspections, piping and pressure vessel corrosion monitoring. Railways, rail inspection, wheel inspection. Tubular NDT, for tubing material, corrosion under insulation, amusement park rides, submarines and other naval warships, wire rope testing for crane wires, mirroring wires, ropeway wires, medical imaging applications. Methods and techniques. NDT is divided into various methods of non-destructive testing, each based on a particular scientific principle. These methods may be further subdivided into various techniques. The various methods and techniques, due to their particular natures, may lend themselves especially well to certain applications and be of little or no value at all in other applications. Therefore, choosing the right method and technique is an important part of the performance of NDT. Acoustic emission testing, blue etch anodize, dye penetrant inspection, liquid penetrant testing, electromagnetic testing, alternating current field measurement, alternating current potential drop measurement, Barkhausen testing, direct current potential drop measurement, eddy current testing, magnetic flux leakage testing for pipelines, tank floors, and wire rope, magnetic particle inspection, magnetovision, remote field testing. Ellipsometry, endoscope inspection, guided wave testing, hardness testing, impulse excitation technique, infrared and thermal testing, thermographic inspection, infrared thermal microscopy. Laser testing, electronic speckle pattern interferometry, holographic interferometry, low coherence interferometry, profilometry, shearography. Leak testing or leak detection, absolute pressure leak testing, bubble testing, halogen diode leak testing, hydrogen leak testing, mass spectrometer leak testing, tracer gas leak testing method, helium, hydrogen and refrigerant gases. Magnetic resonance imaging and NMR spectroscopy, metallographic replicas, near-infrared spectroscopy, optical microscopy, positive material identification, radiographic testing, computed radiography, digital radiography, neutron imaging, SCAR, X-ray computed tomography. scanning electron microscopy, surface temperature, ultrasonic testing, ART, electromagnetic acoustic transducer, laser ultrasonics, internal rotary inspection system ultrasonics for tubes, phased array ultrasonics, time-of-flight diffraction ultrasonics, time-of-flight ultrasonic determination of 3D elastic constants, vibration analysis, visual inspection, pipeline video inspection, weight and load testing of structures, coroscan C-scan, 3D computed tomography industrial core scanning, heat exchanger life assessment system, RTJ flange special ultrasonic testing, personnel training, qualification and certification. Successful and consistent application of non-destructive testing techniques depends heavily on personal training, experience and integrity. Personnel involved in application of industrial Ndt methods and interpretation of results should be certified, and in some industrial sectors certification is enforced by law or by the applied codes and standards. Definitions. The following definitions for qualification and certification are given in ISO 9712. Certification procedure, used by the certification body to confirm that the qualification requirements for a method, level and sector have been fulfilled, leading to the issuing of a certificate. Qualification, demonstration of physical attributes, knowledge, skill, training and experience required to properly perform NDT tasks. In U.S. standards and codes, while a very similar definition of qualification is included in AS&TS-NTTC-1A, certification is simply defined as written testimony of qualification. In the aerospace sector, EN 4179/2009 contains the following definitions: certification written statement by an employer that an individual has met the applicable requirements of this standard. Qualification, the skills, training, knowledge, examinations, experience and visual capability required for personnel to properly perform to a particular level. Training, non-destructive testing training is provided for people working in many industries. It is generally necessary that the candidate successfully completes a theoretical and practical training program, as well as have performed several hundred hours of practical application of the particular method they wish to be trained in. At this point, they may pass a certification examination. While online training has become more popular, many certifying bodies will require additional practical training. Certification schemes. There are two approaches in personal certification: employer-based certification. Under this concept, the employer compiles their own written practice. The written practice defines the responsibilities of each level of certification, as implemented by the company, and describes the training, experience and examination requirements for each level of certification. In industrial sectors, the written practices are usually based on recommended practice SNTTC-1A of the American Society for Non-Destructive Testing. ANSI Standard CP 189 outlines requirements for any written practice that conforms to the standard. Personal central certification. The concept of central certification is that an NDT operator can obtain certification from a central certification authority, that is recognized by most employers, third parties and/or government authorities. Industrial standards for central certification schemes include ISO 9712 and ANSI/AS/NT Camp 106. Certification under these standards involves training, work experience under supervision and passing a written and practical examination set up by the Independent Certification Authority. EN 473 was another central certification scheme, very similar to ISO 9712, which was withdrawn when CEN replaced it with EN ISO 9712 in 2012. In the United States, employer-based schemes are the norm, however central certification schemes exist as well. The most notable is ASNT Level 3, which is organized by the American Society for Non-Destructive Testing for Level 3 NDT personnel. NAVC 250-1500 is another U.S. central certification scheme, specifically developed for use in the Naval Nuclear Program. Central certification is more widely used in the European Union, where certifications are issued by accredited bodies. The Pressure Equipment Directive actually enforces central personnel certification for the initial testing of steam boilers and some categories of pressure vessels and piping. European standards harmonized with this directive specify personnel certification to EN 473. Certifications issued by a national NDT society which is a member of the European Federation of NDT are mutually acceptable by the other member societies under a multilateral recognition agreement. Canada also implements an ISO 9712 central certification scheme, which is administered by Natural Resources Canada, a government department. The aerospace sector worldwide sticks to employer-based schemes. In America it is based mostly on AIANAS 410 and in the European Union on the equivalent and very similar standard EN 4179. However, EN 4179 2009 includes an option for central qualification and certification by a National Aerospace NDT Board or NANDTB. Levels of certification. Most NDT personnel certification schemes listed above specify 3 levels of qualification and/or certification, usually designated as Level 1, Level 2 and Level 3. The roles and responsibilities of personnel in each level are generally as follows. Level 1 are technicians qualified to perform only specific calibrations and tests under close supervision and direction by higher-level personnel. They can only report test results. Normally they work following specific work instructions for testing procedures and rejection criteria. Level 2 are engineers or experienced technicians who are able to set up and calibrate testing equipment, conduct the inspection according to codes and standards and compile work instructions for Level 1 technicians. They are also authorized to report, interpret, evaluate and document testing results. They can also supervise and train Level 1 technicians. In addition to testing methods, they must be familiar with applicable codes and standards and have some knowledge of the manufacture and service of tested products. Level 3 are usually specialized engineers or very experienced technicians. They can establish NDT techniques and procedures and interpret codes and standards. They also direct NDT laboratories and have central role in personnel certification. They are expected to have wider knowledge covering materials, fabrication and product technology. Terminology. The standard U.S. terminology for non-destructive testing is defined in Standard ASTM E1316. Some definitions may be different in European Standard EN 1330. Indication are, the response or evidence from an examination, such as a blip on the screen of an instrument. Indications are classified as true or false. False indications are those caused by factors not related to the principles of the testing method or by improper implementation of the method, like film damage in radiography, electrical interference in ultrasonic testing etc. True indications are further classified as relevant and non-relevant. Relevant indications are those caused by flaws. Non-relevant indications are those caused by known features of the tested object, like gaps, threads, case hardening etc. Interpretation are, determining if an indication is of a type to be investigated. For example, in electromagnetic testing, indications from metal loss are considered flaws because they should usually be investigated, but indications due to variations in the material properties may be harmless and non-relevant. Flour, a type of discontinuity that must be investigated to see if it is rejectable. For example, porosity in a weld or metal loss. Evaluation are, determining if a flaw is rejectable. For example, is porosity in a weld larger than acceptable by code? Defector, a flaw that is rejectable that does not meet acceptance criteria. Defects are generally removed or repaired. Penetrant stinger, non-destructive test typically comprising a penetrant, a method of excess removal and a developer to produce a visible indication of surface breaking discontinuities. Reliability and statistics, probability of detection tests are a standard way to evaluate a non-destructive testing technique in a given set of circumstances. For example, what is the POD of lack of fusion flaws in pipe welds using manual ultrasonic testing? The POD will usually increase with flaw size. A common error in POD tests is to assume that the percentage of flaws detected is the POD, whereas the percentage of flaws detected is merely the first step in the analysis. Since the number of flaws tested is necessarily a limited number, statistical methods must be used to determine the POD for all possible defects, beyond the limited number tested. Another common error in POD tests is to define the statistical sampling units as flaws, whereas a true sampling unit is an item that may or may not contain a flaw. Guidelines for correct application of statistical methods to POD tests can be found in ASTM E2862 Standard Practice for Probability of Detection Analysis for Hit-Miss Data and MILHD-BK 1823A Non-Destructive Evaluation System Reliability Assessment, from the U.S. Department of Defense Handbook. See also. References. Bibliography. External links, Ndt.net, Web's largest database of non-destructive testing, the International Committee for Non-Destructive Testing, European Federation for Non-Destructive Testing, American Society for Non-Destructive Testing, Inspectioneering Journal, trade journal that publishes NDT news in the oil and gas and chemical industries, NDT Education, University of Iowa Repository for Non-Destructive Education Material, ndt.net, Non-Destructive Online Journal, ndt.org. NDT Jobs, News, and Social Network, ntki.com, Non-Destructive Testing Wiki for Professionals, simply ndt.com, NDT Employment, News, blog website, MILSTD 271, Requirements for Non-Destructive Testing Methods. United States Department of Defense June 27, 1986 TO33B1-1, Non-Destructive Test Methods, Basic Theory, Technical Manual. United States Army June 15, 2007 mtarotech.com, the online community for aerospace NDT professionals, Topazitk,